Thank you for the introduction, Monitomo Sensei. Sorry if you will be using English in my presentation today. I myself, as Monitomo Sensei explained, graduated here from Hokkaido, from his lab, so it's always fun to be back here. I will be speaking today about some efforts that are happening in REEC and RCCS, and also extending to collaborators outside REEC and RCCS to scale AI for science on Fugaku and outside Fugaku. First, I have to mention that here is a summary of the collaborators, not all of them. This is not an extensive list inside Japan and outside Japan, where I'm basically presenting on their behalf. I don't think we need to spend so much time to explain what Fugaku is. It's a flagship system in Japan. Currently, it sits on the second system on the top 500 list, which is operated by REEC and RCCS in Kobe. It is planned to be used for scientific computation, obviously, and there has been a push in the last year or two or so to also have what we call virtual Fugaku, and this is an attempt to have an extension of Fugaku. It's not particularly limited to AWS, but this is a choice we made because AWS has also ARM processors, the Graviton series, so it's more seamless for users to be able to transfer their work back and forth. So now we're exploring a lot in that area. So workloads can be moving between a Fugaku and the system. So those are some highlights about research efforts that happen in Fugaku. It excels pretty well for benchmarks in HPC world. As Kota Sensei was mentioning in the previous presentation, maybe in LLMs, there's a different type of benchmarks like Open LLM Leadership Board. But since this is a system that was primarily designed for HPC, it performs pretty well on the top benchmarks we expect. That led to some interesting research, like Gordon Bell Award for COVID-19 research, a lot of research in many directions, in which the next few slides I will try to summarize. So from now on, the presentation is two parts. In the first part, I'm giving a very high-level overview of some of the AI, of some of the science enabled by AI on Fugaku. And then in the latter half, I'll focus more on the effort of my team at REEC and RCCS. So this is the next few slides, not work by myself. It's just a collection of slides showing efforts by REEC and RCCS teams and what we call priority applications, or applications that took priority when Fugaku came online. And all that work is summarized in a bookshop that appeared last month. So one example is, for instance, early on work, which REEC started early on as soon as we got our hands on Fugaku, which was trying to use AI for simulating 3D flows in cylinders. And this is particularly important for people who do a lot of CFD fluid dynamics, like car design and such. And as you can see, even the model looks like what looks now like it's pretty primitive, but at the point that was like state-of-the-art convolutional neural networks like. The second work, which from Nomura Group, I think it's interesting because this is trying to use AI to what happens if flooding happens, because most of Japan is in coastal cities and towns, and floods can happen a lot, especially in the rainy season in Japan. So what this tries to see is what if we have a assumed flooding, and how can the AI prediction be close to that if a tsunami happens, for instance. This was particularly important and even pretty highlighted as a priority application by the Cabinet Office in Japan, because this is where exactly the combination of AI and science on high performance computing can lead. And again, at the time, this is maybe like 2.5 or 3 years ago, the AI component with it was pretty not so advanced by today's standards. But again, it just kind of ignited interest in going in that direction. Another example, which comes from cancer research, and this involved company in this case, which is Fujitsu, plus also researchers from RCCS. And it's looking into the causality of, or particularly what kind of genes would cause resistance to drugs used to treat drug cancer. And this was an important step because early on, one of the very famous applications, even in DOE, Department of Energy, Exascale systems, use what they call Candle. Candle is software based on AI, it's trying to use it for cancer screening. and a lot of effort was in that direction. And so it took a long time in that direction to prepare the software stack for it. So it's a notable effort. Another example, which comes more from classical basic science, which is trying to understand more what happens in the explosion of supernova, and basically it's trying to take a ground truth reality and predict what happens from spectral analysis of data in the explosion of supernova. That used, again, like the previous works and previous slides, what we consider now a simple deep learning model. But again, it took a lot of effort initially at this point because Insianians for 3D input was not a simple thing to do, and it used a combination of recurrent neural networks and convolution networks. And there are other slides, but again, this is just slides to motivate the book chapters, collect them, but I will just go through some of them where Fugaku was not directly used, or at best it was partially used, but nonetheless, it was an effort by Ricky AXIES researchers and collaborators. And this is by Yukoya Sensei, and this is again looking into simulate what happened and the flood and debris. So when flood happens, what follows later on that a lot of debris would move. So you would want to understand and model these phenomena. The thing is, it could generate, and this is actually a very important thing in scientific software. Unlike in traditional applications in industry care about for AI and machine learning, for example, natural language processing or image analysis, you have to collect and gather data set and clean up, as Jikota Sensei, for example, was speaking in the previous presentation. But in scientific applications, in a lot of these situations, you can generate the data as much as you want from models, which is a very good thing because it means you can have the data on demand, you can prepare it in the way you want, and you're sure it's clean and labeled. And this is what was one of the very first few projects that explored that direction, that use your own models, not to do the computation, but to generate the input for the AI itself. So it becomes like a seamless workflow as you move simulation to the AI. Another work which again used for compression. I will not from now on focus much on the exact applications. I'll share the slides gladly with anyone, but they cover a very wide spectrum of applications, like the previous one was compression. This one is how to encode quantum states, which was pretty important because this problem is notoriously very compute intense if you would want to simulate, because the cost of memory grows quadratically with your problem size. So we want to use exact AI in these kind of situations. And a big list that I'm trying to summarize. It's just not even a conclusive list, but I guess it says the mode and explains that early on, since Fugaku came online, people have been knocking on the door and exploring how can it be useful in AI context more and so on. I will switch now a little bit to, instead of now give an overview of how a lot of teams in RIKEN and collaborators in other RIKEN organizations and also across universities in Japan and outside are interested in deploying more AI for science. I'll focus more on the team I work in, which is high performance or special intelligence system research team, and how we're trying to do our little bit of contribution to help the teams be able to do that. Before I move, the team consists from a lot of members that I have to mention all of them. Includes like full-time researchers, visitors, and interns, and so on. Without them, of course, none of them is possible. So our main research aim in three things. One is how to scale AI on nodes of Fugaku. If you want to scale AI on a system, as Yukota Sensei mentioned in the previous slide, Fugaku has 159,000 nodes. How do you scale AI for that? And this is one of the missions that started early on since Fugaku came online. But then the two main things the team are trying to do is what we call HPC in AI. Like, in a sense, how can HPC knowledge we know be used to scale AI, increase the parallelism, be more efficient, and reduce the latency? And then the other side of the equation, right? If AI is to be successful, why not use it in HPC, in scientific applications, right? It kind of makes perfect sense. Can it be used in life science, physics, and CS and math, and engineering, and so on? And those are some of, for example, applications we care about. So this is mainly the mission of the team. So in the next few slides, I will explain a little bit briefly as we go down from the main aims 1 and 2 and 3. First, for scaling AI to nodes of Fugaku. Now, this was really a big challenge because Fugaku was designed somewhere, or the feasibility study was somewhere between 2012 2014, right? This is where the whole thing about the revive of deep learning happened in 2012 with AlexNet winning the competition and showing that deep learning finally can be a competitor to other AI methods. When Fugaku was designed, that was entirely not in the picture, right? And if you look at the priority issues for Fugaku, those were selected. At the time Fugaku was designed, it was called PostGate, the predecessor supercomputer. None of them have AI. Even the word AI or machine learning doesn't even exist, right? So it was a big effort because that meant we have a system that is not designed for machine learning workloads, it's designed for general purpose HPC, but then you have to make it work for AI. This took a lot of effort to understand the real prospect and increase interest and efficient machine learning. And it has been an ongoing effort we even haven't finished yet, which involved many parties from inside RIC and RCC and outside, and also in collaboration with industry, particularly ARM and Fujitsu, to create a deep learning ecosystem for Fugaku so that we can be able to use it. Again, this is past an ongoing effort that has taken a lot of time on our side to be able to do. We were able to push some good results on MLPerf. Training HPC is a go-to benchmark when we want to benchmark systems for AI workloads, not specifically large language models. It has a collection of different types of problems, and Fugaku is now sitting on that list. But again, there's too much work to improve. So this was the first part, how to scale AI. And currently the stage we're in, which was mentioned briefly by Kota Sensei, the previous speaker, we're looking at a project of GPT Fugaku, in which now that we can scale, can we have distributed training of large language model with massive scale? This is a big effort. It's led mainly by Professor Kota, and with a lot of engagement, of course, from RCCS teams, industry, and also outside Japan, our partners, how to be able to distribute these workloads of AI in a way that fits on Fugaku and even at the node level. So how can you have vertical scaling and horizontal scaling? Because again, the system was not designed for this workload. That's the first part. I will now shift gears a little bit to speak about, again, we had three things I wanted to cover. This was the first one. Now I'll focus a little bit on HPC and AI and AI and HPC. So as for HPC and AI, one interesting thing is that in traditional high-performance computing workloads, depending on the compute pattern, usually you have one or two bottlenecks at most. So you can know, for example, if you're doing a lot of PDE solving applications involve finite difference methods that you're memory bound. So you optimize a lot on how to get most efficient locality and memory use. In some kind of applications, you know you're AI bound. Some other applications are network bound. But it's pretty different in AI, and by AI I now mean mainly deep learning. Is that you don't have a particular application. Like you can have multiple bottlenecks, so we have to approach different bottlenecks at different levels in the stack, because depending on how you configure your problem, you can be bound by capacity, by memory bandwidths, by I/O, by throughput, latency, network, and compute. And here I have a little slide before I move that was slightly also covered by Professor Kota, which is note that also this is one challenge, that you don't have a single bottleneck, right? The other challenge is HPC applications that took 40 or 35 years, like the age of modern HPC, have rode the curve of Moore's law. So they're tracking Moore's law. So if you have an HPC application of, for example, working on some physics and mesh that presents some problem, every time you get a bigger system or a faster system, you also increase the resolution of your problem. So they track, they go hand in hand. You can almost plot actually the resolution, for example, of weather and climate models in a graph. And if you put next to it the increase in processor performance for Moore's law, they map exactly. What happened in machine learning is that you basically compress all that stuff in just 5 years. So in 5 years, this is a slide collected by Nikolai Dryden from Livermore, one of our collaborators. So from 2017 to 2023, not that this is log scale, okay? You went from the very early models, right? Like transformer, basically, right? Where you had, how many parameters? 200 million parameters or so, all the way to what we have now, like GPT, and this is even not the latest. It's actually higher than that. You went to the range of hundreds of billion parameters or even trillion parameters. So that meant you did 10 to the power 6x scaling in 5 years. It took other applications in HPC 35 or 40 years to get that level of scale, which is what you get with Moore's law, right? So this also was the main challenge. How do we scale that much? Like 1 billion times in just 5 years, right? A question that I get a lot, and actually I think it's important also to clarify, why are these models even big to begin with, right? Why are these all parameters? Especially if someone in the crowd comes from the background of myself, at least my background in combinatorics, and you always think, why do you need all these parameters? There's a famous saying by John von Neumann, the famous mathematician and scientist, which said, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. Which is, he said it as a joke. Actually, some people took that and they wrote the paper on it. And you literally, if you have 4 parameters, you can draw an elephant like that, have a function. And if you have a fifth, you can really move wiggle its trunk. That means you can do so much with a few parameters, right? So why all these billions of parameters? The reason is because over-parameterized models are effective, right? Maybe you don't need all these parameters. Maybe you only can have some sparse connections that are enough to learn. The issue is you can't really predict those sparse connections. So yes, the models are over-parameterized. You don't need all the parameters. You need some of them. How do you know some of them? If you need to learn the connection, that means you have to compute all of them. Then it defeats the purpose. So the reality now is we have very over-parameterized models, and they work. And what makes it worse is there's something called the scaling laws, as listed in this paper in Europe a few years ago, that says that your data should be proportional to the model size. So if you know that the model must be big, right? Because overfitting works. Some people showed that. But that means also you need a lot of data to go with it. That means the data set grows with the model and vice versa. And there's no exact ratio. There's some people who say 1 parameter per 3 samples, or 1 to 10, or 1 to 20. And you can track it if you look at large language model, but there is a proportional value here. So in summary, you have exponentially growing models and data sets. They stress the subsystem in a supercomputer in every possible way. And again, the challenge that you can have different bottlenecks. And it depends on the scale of the model and strategy. So in small to large scale training, you can be bounded by memory capacity. And that, for example, if it's a large language model, means models up to say 7 billion, 10 billion, or even 17 billion parameters, you can be bound by memory capacity. If you have large, medium, large scale training, like some of the AI science applications that show early on in early slides, you can be bound by the I/O itself. If you have large scale training and you have a large model, you need to change all the parameters, then I/O and communication can be a bottleneck, and you can suddenly realize that 60 or 70% is lost in communication. It could be compute also, if you use unusual matrices shape. Or it could be latency. It really depends on this. How do you define the particular problem, scale, and model? That means you need to optimize across this entire stack, basically. So I will not go into details because it's for lack of time, and also I guess more details will not help here, but I'll just summarize a little bit of the work we had to do in our team to be able to scale. So one of the works, for example, had to do out-of-core training, meaning that you do all this offloading to CPU memory when need be, and you fish the data back in, and this is basically allows you to increase your memory capacity by going out of core. It sounds like a standard practice now, and in fact, like the deep speed library, which is used in training, GPT and ChatGPT have that in production, but this was pretty much in 2020, like a paper in SC was maybe the first production quality level of it, and actually deep speed kind of endorsed this same method. Another is to analyze all these parameters. Like we said, there's a lot of parameters, and this work was done jointly in the lab of Monotomo Sensei here in Kodai, on how would you do landscape analysis. If you have a lot of parameters you cannot visualize, are there ways where you can personally look into some of them? In other work, we needed to understand the parallelism, what happens, because there are many different ways you can parallelize when you are scaling. So we needed an oracle or a cost model to drive that. Another is, okay, maybe we cannot scale in many reasons, in many scenarios. How about we look at the deep neural network as a graph? It's a computational graph at the end. Can we take this graph, because in HPC we know data graphs a lot and how to parallelize graphs. Can we take it as a graph and just do graph partitioning on the amount of work we have, such that on the nodes we have, or resources we have, or GPUs we have, such that it's agnostic to the user and easy to work with. In other work, we looked into actually more down in the stack. If you would design a network that would work for a system that is mostly doing these AI deep learning training workloads, which means it's an all reduced compute pattern, how should it look like? Because we know that the ring-based algorithm gives you high latency, and this work led into that. And actually, some of the very newer work after that came from labs like Thorsten's lab in ETH and so on, that is proposing humming mesh and so on, or these kind of torus-based alternatives are basically an extension of that, which just try to optimize the network so much on all reduce, because an all reduce in the end, in an efficient way, is implemented as a neighborhood connection with your neighbor in a ring-based system. And other work, we looked into the I/O. We said, okay, in scientific applications, it could be that the training is not a problem at all. In large language model, if you're training on text, your input is not that huge because you're using text corpora and they're pretty dense, right? In information, not so dense. So it's a few terabytes basically for your entire data set, right? But in scientific applications where you're training on, for example, high resolution images and such, your bottleneck is just to move the data from the storage system to get it, and then you do the training. So that looked into a way where you can do eliminating this bottleneck, but what we said shuffling. So instead of using the I/O, you do the exchange over the network to reduce the bottleneck. In other work, we looked into more lower level, that the building blocks of these deep neural networks in the end are just very dense matrix multiplications. Can we make those faster or not, right? Convolution kernels were represented in as dense gems. Same also if you look at the attention-based models, maybe it's matrix multiplication, matrix vector, but in the end, it's dense linear algebra. So can this be optimized or not? And we looked into that work and into that also. In another work, we looked into multiple GPU communication. This can be a bottleneck because nowadays, if you look at GPU-based systems, they're usually made of nodes that have a lot of GPUs. Total 8 GPUs and maybe 16 if you're using pods, what's in NVIDIA called super pods, like DGX boxes. Can you reduce the communication at all? So all the communication is driven by the GPUs. Other ongoing work, we're looking for ultra-long sequence for transformers. Transformers, as Ricotta mentioned earlier, are basically the architecture that's used in large language models. And one issue with them is that the cost of compute and your memory requirement are quadratic to the input sequence size. Why do you want long sequence? Because the longer the sequence, the more long-range relations or patterns in the data. And to find more patterns in data in longer sequence. And this is a main issue that's meeting everybody in industry and also in research, and how to increase size. And there's a whole long ways of approaches to do that. And one of the approaches we look into it is how to actually take that workload and parallelize it across GPUs. And we were able with that to go to context lengths of more than 100,000 tokens, basically. And I think for ourselves, this would be useful as we go into scientific applications. And also, I think outside that, in NLP, it would be very useful. In another work, we looked into elastic dynamic machine learning because large language models are pretty static. So it's an iterative process to train them. You have a model, it's already designed before you start. You're streaming the data in, and you're just feeding it the data in batches or in iterations. But what happens if your model is dynamic? Because there's a whole big range of reasons why a model would be dynamic. It could be a choice of you to make it more efficient, to make it sparse so it's dynamic, or it could be a feature of the models. The model internally has components for experts or mixture of experts, which makes the compute vary over time, which leads to load imbalance. So how can you resolve that load imbalance? And this is what we look at, how to have elastic pipelines. This is work under review. More on related works we're trying to look at from different angles is how to use a transformer to model some of the high accuracy imaging painting. This is more like an application direction. How to adaptively hide samples in training, which we're looking at. I will shift a little bit to the part I think that is actually more relevant, which is not HPC AI, and a lot of people are trying to apply HPC best practices to scale AI. But the real promise for the community would be AI and HPC. Now that these methods are gaining more attention, they're becoming more robust, becoming more reliable, can we use them in HPC? And HPC here means scientific simulation or AI in science, basically. It has a big potential. Of course, there's a lot of hype, but it has a big potential. But it requires full engagement with collaborating domain experts. And this is actually a real struggle to find projects and scientists who are willing to explore these science things. So we have several ongoing projects in the team that covers different aspects from life science to physics to engineering, with organizations inside Japan and outside. That yielded some good results. For instance, we were able to use AI to replace the image drag decomposition, which is an important thing in typographic image reconstruction, which is a very important application in people who try to reconstruct images from scans. And it's used widely in centers in Japan, like Spring 8 facility, Synchrotron, and also outside in Oak Ridge National Lab and Aragon National Lab and several centers around the world. And we were able to see that using AI in this particular work, which was in ST last year, published, was able to actually improve a lot. In another level of another kind of work, we looked into, okay, how we can improve the predictive performance from aqueous solubility, so it's solubility of solutions. And this paper was really a learning experience. This was in Nature Scientific Data last year, because we realized that it basically was a paper working an entire year to just create a data set. It was very hard, harder than we imagined. It was a learning experience to know that just creating a data set, cleaning it up, because there's so many data sets on solubility available out there, and there's so much redundancies, there's so much overlap, and they're even designed and labeled in different ways. How can we make a data set to show that the data set itself, when you train with it, will be able to outperform the analytical and empirical methods that would predict how soluble a new compound would look like. So I think this was an eye-opener for me and everybody involved. It meant that a lot of the work happening from now on will be in engineering data sets, how to create data sets that are engineered in a way you can use. A project that is very promising we're working on, which is collaboration between Aragon National Lab, Riken AXIES, and Spring 8, is trying to look at high energy physics, understand more about particles, in this case in particular. How can you understand like the proposed, so basically there's no pictures of protons. That's the issue they have. They have devices which they do like particle bombardment and generating they do a bombardment and generating results out of that are just samples and events. They want from that to reconstruct an image which needs an event level inference framework. And this is basically what we're trying to do. We can't predict the quarks directly coming out of this interaction, but can we, from samples, construct images? And this is motivated by, for example, what happened exactly and the definition of photons when they recreated an image for the black holes. This is proving very hard because in this specific case, they have very high strict requirements on quantifying uncertainty. You can't just use AI, throw stuff at it, and it will predict for you, and you just take it and walk. Physicists would need to generate probability distributions that they have confidence in, and they can put a number on how to quantify uncertainty. So one of the efforts here in this project that we are currently working on in RCCS is, can we use an ensemble of machine learning models to try to get a range of outputs, and from that we define uncertainty. And I think moving forward, this is a big issue for AI, for domain expert scientists to absorb AI or willing to embrace AI, that they cannot, in many cases, just accept the results without being able to interpret it. And moving forward, I think this is an issue for a lot of people in that area. Finally, the slide I just closed with, this is also an ongoing project that we're very excited about, which is pretty ambitious. It's a perfect combination of what modern AI and large language models are capable of doing, plus HPC compute. So resolution of the mouse brain MRI images. For humans, you can have low resolution, you can't have high resolution because you can't expose humans for a long time in an MRI scan. But we have been keeping like very fast, up to 5 microns. And this is actually data sets available in Duke University. It was a breakthrough basically in that field because they have designed a reliable MRI device. It's diffusion MRI, by the way, also that can work on this resolution and give you results without artifacts in it. The question is, at this resolution, you basically have connection at the level of neural cells, right? So the question is, can we take that, and this is in the end a 3D image, volumetric image, can we do very high resolution segmentation to be able to identify all the connections in the brain, and to get what's called cellular connectin. Connectin is basically the wiring of this brain, because this has been not solved problem. So far, there's models of it, or there's high coarse-grained models of it, but there's nothing high resolution. And the question is, can we use AI methods, large language models are proven effective to work in resolution of images. There's problems you need to solve, like the long sequence and so on. But can we combine both of these things together and show that this is a point where the understanding of the brain, instead of relying on simulations, as it has been classically done in the last 30, 40 years, but it would rely on actual real empirical ground with data. So the wiring is not just modeled in a simulation, the wiring that comes from actually segmentation on real images that you have captured. Again, this is an ongoing project we're excited about. I said it's a final slide, but sorry, there is another final slide. I forgot. One also issue we're looking at is actually using AI for scientific codes, right? A lot of, maybe, I don't know, maybe 2/3 of the time of the HPC community is just to take scientific codes, tune them, optimize them for new hardware. And you have to repeat the process every time a new supercomputer comes out. The question is, there are compiler technologies. Compilers should be capable of generating code, but they cannot make assumption on your target hardware, right? There are high-level code transformations we know about that have context, but they don't work on your specific problems. And there's auto-tuning methods, which you give them code, and you give them hardware, and you say auto-tune the code, the parameters, to make it run as fast as possible. Each one has its limitations. So the question is, in this work, can we combine machine learning here, in which we can get a code that is auto-generated for your hardware? So if, for example, a scientist wrote a scientific simulation for Fugaku, which is made up of ARM processors, and in 5 years we have a new supercomputer that's made up of a new different technology, different type of CPU or even GPUs. How can you take that code and change it in a way that the programmer who is a scientist does not have to rewrite his code again? So this is something also we're working on in very early stages. With that, I just have to say there's very big announcements soon coming from Riken RCCS on AI for Science to have a big push and initiative that is nationwide, not just limited to Riken or Riken RCCS, in which we hope to see more and more of these AI models, large language models, not just large language models, there are a lot of different ways to do machine learning to be useful in science. So we start to see impact being delivered in science. Of course, it's important to have impact in industrial applications or commercial applications, but also impact in science is what we care about. And with that, I would say thank you.